Throw it up, watch it all fall out. Blow it up, that's how we ball out. Throw it up. Wake up in the morning feeling like P. Diddy.
Hey, what up,
Grab
girl?
my glasses, I'm out the door. I'm gonna hit this city.
Let's go.
Before I leave, brush my teeth with a bottle of Jack. Cause when I leave for the night, I ain't coming back. I'm talking pedicure on our toes, trying on all our clothes, boys blowing up.
Bernoulli's principle states that the pressure in a fluid decreases as the fluid's velocity increases. In this case, the water is moving at a higher velocity than the air, so the pressure in the water stream is lower. The higher pressure air, therefore, pushes the balloon into the stream from the faucet. Another example of Bernoulli's principle can be seen with two balloons suspended in air. Flowing air in between the balloons decreases the pressure between them, so the high pressure air on the outside of the balloons pushes them together. This is just another demonstration that displays Bernoulli's principle. The hairdryer produces a flow of air with a higher velocity and lower pressure than the air surrounding it. The ping pong ball stays in the flow from the hairdryer even if you tilt it side to side a little, because the air around it pushes it back into the stream. Airplane wings are designed to work on Bernoulli's principle. They are designed so that air flows over the top of the wing at a higher velocity than the air that goes underneath it. This higher velocity results in a lower pressure on top of the wing than the air underneath it. The air underneath the wing pushes up on it and creates lift, allowing the airplane to fly. By blowing on the top surface of a sheet of paper, the sheet rises as a result of the lower air pressure above the sheet.
This experiment demonstrates surface tension. The cohesive forces between liquid molecules are why the water will not leave the bottle even though there is a hole. The molecules at the surface do not have other like molecules in the air, and so they cohere more strongly with the other water molecules.
Air is held to the earth by gravity. Gravity pulls air downward, giving the air molecules a weight. The weight of the air molecules exerts pressure upon everything. When the candle burns, it heats up the air in the jar. This hot air expands, and some of the air leaks out of the bottom. Once the oxygen is gone and the candle is out, the inside air cools, causing the air outside to contract, creating low pressure. While the outside pressure, also known as the atmospheric pressure, forces the water into the jar.
This demonstrates adhesion between partially wet, solid surfaces. The liquid displaces the air in between the cards, and the water on each card adheres, explaining why the cards do not separate when wet.
The ideal gas law is an expression that relates the volume, pressure, and temperature of a gas. If the temperature of a gas increases, the volume and pressure of the gas also increase. This
can be observed by placing a balloon over an empty water bottle and heating the water bottle over an oven. The pressure of the air increases, and so does the volume and pressure, which can be seen by the balloon inflating. When running the bottle under cold water, you can see the volume decreases because the temperature decreases too.
We perform this demonstration to show Archimedes' principle, which states that the buoyant force exerted on an object is equal to the weight of the fluid that the object displaces. First, we mast a cap to a peanut butter jar, which is going to catch the displaced water. Then, we mast the object, which was right around 100 grams. Next, we masked the object while submerged in water and collected the water that was displaced in the process. By taking the mass of the object out of the water and subtracting the mass of the object while in the water, the result is equal to the weight of the water that was displaced.
This experiment demonstrates air pressure and the fact that air has mass. With air inside the bottle, it has a mass of 11.7 grams, and with no air, a mass of 10.7 grams. This shows the mass of the air in the bottle is 1 gram, and the bottle's weight in pounds remains constant until its mass changes.
Pascal's principle states that pressure applied to a closed container is transmitted equally to every point of the material and walls of the container. This principle is used every day when squeezing toothpaste.
This experiment demonstrates how the density of a liquid can determine whether an object will sink or float. An egg is placed in a glass of water and sinks to the bottom because it is more dense than the water. A second egg is placed in a glass of water that has salt dissolved in it. The salt dissolves in between the water molecules, making it a more dense liquid, so the less dense egg floats on top. The third glass is also filled with salt water. By pouring out some of the water and placing the egg in the glass, and then pouring fresh water with no salt in it, the egg floats in the middle of the glass. It is less dense than the salt water, but more dense than the fresh water.
If the weight of the body is less than the force of buoyancy, then the bottle will float. If the weight of the body is equal to the force of buoyancy, the bottle will neither sink nor float. If the weight of the body is greater than the force of buoyancy, then the bottle will sink. When you use your thumb to block the end of the hose, the thumb blocks the area the water can exit. Therefore, the water exits the hose at a higher speed. This is shown by the continuity equation that implies that a fluid is faster in narrow areas as opposed to wide areas. The reason you are able to flip the cup upside down is because the air pressure outside the cup is greater than the air pressure in the cup. Because there is no air in the bottle, there is no air pressure and the water remains in the glass.